This is the last part of the operating system management. If we have a time, we can discuss a more advanced topic, which I prepare, but probably because of the snowy day at the beginning of the semester couple of time, I don't think we can cover the additional topic, but at least I'm going to cover up to the chapter 13, which is mostly discuss about the file management. Okay, so first part was the process management and followed by the memory management. Third part is the file system management, how to manage the file. These three are the main components of the operating system, also main the topic of the operating system class. So in chapter 10, I think we have something little bit remainder. How can I engage? I do not know how to exit. Okay. I think that we had several slides from the chapter 9. It's about China. Oops. What happened? Oh yes. Okay. So we have mostly talked about how to replace the page. In other words, how to find the victim page from the full of the page frame, which means the physical memory. So first we have used the first in, first out. Okay, first in, first out, which means the victim page will be oldest one. Okay? So that's simple, but sometimes it may cause the delayed anomaly depending on the pattern of the data. So the best performance is you can find it from the optimal algorithm. So you can see the future. If the page is not used, it will be the victim page. Otherwise, we'd better keep for the reuse. So that is the optimal algorithm problem. So it's not possible to see the future. So optimal algorithm usually used for reference, which means when you compare your algorithm, so how much close to the optimal algorithm. Okay, so that we have discussed about the LRU algorithm instead of taking a look at the future. Why don't we see the past before? And if the frequently used before, we better keep. Otherwise, we can select the victim page. That is the LRU algorithm. The problem is how to implement a counter or the history of the each frame. So there are different techniques. So we can use for each page frame, we can keep the counter, or we can use the stack area. So using the stack, we can have only one data structure. Still, the least recently used algorithm, LRU algorithm, is not easy to implement or more complex. So we can use the LRU approximation. Okay, so which means that we can use a reference bit. So we can see if the page is a reference, we can assign the 1. Then we can use the instruction or shift instruction. Then which can be processed very, very quickly. So we can just compare the highest number, most recently used one. Otherwise, the smallest number will be victim page. That is the LRU approximation. There is another variation of the LRU algorithm that is a second gen. So we can have only the one reference bit for each page, then we can take a look at the side or circular fashion. Okay, if that is the one, it can be the if that is reference 1, otherwise 0, so we can check the 0 or 1 circular fashion. Worst case, we can turn around just one time, and next time the first one will be between pages. So it's a second. That is the reason it's a second case. Okay, so there are ways to implement enhance the performance of the page replacement. So we will see. This is allocation. So we have discussed about the global allocation and local allocation. So we can allocate the page frame for each process. That is the local allocation. Otherwise, if we generally use it, it's a global allocation. Also, we have talked about the thrashing. Thrashing means if a certain time the number of page fault is the increase, then CPU utilization will be dropped. Okay, that is called the thrashing. Why thrashing will be happen? Because of the repeat of the pattern. Okay, at that time, if you do not have the enough free page frame, it will be every instruction, every page. When CPU refer the page, it will be page 4, page 4. So this is a typical example of to describe the thrashing. So we mostly, if we have the page frame, so maybe fine, but because of one missing, so it's repeated every time, it will be page 4. How can we address such a problem? We can use the locality. We can make them group. So for example, the slide shows the thrashing. Thrashing means it's a CPU utilization is good because the CPU utilization is high, but certain time it's drop because of a lot of page fault. Okay. So we can use the locality model. Okay. So how can we find such a group of the pages? So this is the x-axis for the time. Along the time, this is the y-axis shows which page are reference. So you can see some group of these pages, so we can make them group. So we can reduce the number of that. So that is called the working set model. So this one will be repeated, so we can make them group. So if they are needed, we can page in all together. Okay, not one by one. That is the idea of the working set group. Okay. Memory map, the file is anyway, so when we read the data from the file, okay, that should access the hard disk drive and through the disk controller, hard disk drive controller, then get back to the memory. At that time, why don't we, if you read the data frequently from the hard disk drive, why don't we assign specific pages for the file? Read or writing the file. Okay? Then it's kind of dedicated from the file to the page. That is the memory map the file. Then we can reduce the number of the page fault by assigning to the file to the specific dedicated memory page. That is the memory map the file. So there are other some factors that we need to consider when we discuss about the paging. First one is a pre-paging. Pre-paging means even when you find the victim page or when you allocate the page to the specific map, the process, it takes up time. So why don't we, when operating system starts, for example, why don't we allocate the specific area, specific number of the pages for specific program? Like the kernel program is also, the operating system also, or application program also. So it's a pre-pages. So by assigning the pages for the specific program, we can increase the performance. That is the pre-paging. Another issue is the page size. So page size, we didn't discuss a lot for the size of the pages, but that is the basic I/O, right? To the page in, page out. So what is the optimal size of the page? The bigger is the better, or the smaller is the better? You cannot say. It depends on the application or operating system type. For example, if your operating system need the fast response time, such as online transaction or the web server or something, the banking system, the user, client, they don't want to wait for a long time until the system responds. At the time, if you have the bigger size of the page, you can keep less number of pages. It takes a longer time to page in and out. So at the time, you'd better have the smaller size page. On the other hand, if your operating system mostly process the batch job or data warehousing job, it's a long-running job during the night. At the time, if you have the smaller size of page, it has a lot of page in and out, a lot of page for it. It's a waste of time, overhead. So you'd better have bigger size of the page. However, it's not easy to determine fixed size. So current operating system provides sometimes the double, dual size. So it has a 512 byte the page size as well as the 2K. So depending on the application or the time or by the operating system, it can be in the interchangeably. We can use the different size, but mostly they are the power of 2, which means 2 to the power of something, because it anyway is based on the basic the operating system I/O. Also, to avoid such a page fault, we have discussed about this one in the programming level. In the programming level, so if we understand the concept of the page fault, there are 2 typical examples to handle the array 128 by the 128. So you should understand what's the data structure for the process. In the process, if you allocate the array, what happens? Is it located in the heap area directly? Such an array will be pointed from the heap area. For example, if you have something processed, this is a heap and this is the stack. So instead of allocating the integer 128 by 128, it has the pointer. Then this pointer is the 1, 2, 3, then the next, this one. So in this case, if you read the I, okay, first J, for each I, okay, for each I, first the J. So J is here. Why don't we take a look at this one? For the I is a fixed, and then for this 128. Then I is 2, 128. So if you have the page for this worst case 128 pages for I. However, in this case, this one is the for each 1, 2, 3, 4 is a page 4 and page 4, page 4. So in worst case, it will be 128 times 128. Page 4. That is the reason. So usually the outer loop will be used for the first array. So intuitively, many developers use such a way, but sometimes what if change it? Output is the same, but the performance may be different. That is the program level, the issues in page replacement. Okay. I'm going to skip the operating system example. You can, based on the previous one, you can understand the example of the page replacement and virtual memory management. Okay.
Rosa, can
Yes.
you just quickly explain once again the page grouping?
You mean the working set model?
Yes.
Working set model? So working set model. This sometimes because of the page 4, like this in this case, is every page. Every page, whenever you access the data, there is a page fault, right? So huge number of page fault, which means the CPU cannot do anything. That situation is called thresh. So how can we avoid such a thresh? So why don't we make the group of the page instruction, then load together, which is called locality. Okay. So the problem is, how can we find such a locality model? So sometimes we can analyze which page is left first, okay, something like that. Then we can make these 3 pages as a group, something like that. So that is called the working set model, which is repeated. Like for example, 261577775 is the repeated. So why don't we make them group and load together? Then to avoid the unexpected page fault. The problem is how to find such a working set model. So there are different techniques. This is one of them to find such a working set model.
So are we saying that that set is repeatedly being used?
Yes, they are working together. Locality. Okay.
So we group them.
Yes.
So operating system sees the pattern.
Yes.
Number of pages are working together, then it generates a set.
I don't know exactly what kind of algorithm I use. This is a typical example to find a group of working set, but there might be something the pattern recognition technique to find such a working set.
And you said locality is that we find the group.
Yes, they make them group and put together. Okay. I still can use how to use the new device. Why it shows. Still don't understand how it works. Okay, so today we are going to discuss about the file management. The first one is the master storage system. So when we discuss about the computer architecture at the beginning of the semester, it has the mainly CPU. CPU can process the instruction your order. Okay, then using the bus, you can access the data from the CPU to memory. So memory mostly the organized based on the address. Then, however, memory, the main problem of the memory is the limited the space, and also without power you will lose the data. So you need to keep such information in the hard disk drive. So in other words, when you execute the file, when you execute the instruction, you need to bring the instruction, set of instruction from the hard disk drive to the memory, which is called the processor. So today we are going to talk about how to organize such a physical level of the file system. So file system itself is a software, it's a logical level where such a file system is stored. It's a hard disk drive. So mainly we will talk about the hard disk drive. Okay. So what is a hard disk drive? What about this kind of the tablet or this one? Does it use the hard disk drive? What about your laptop? Does your laptop use a hard disk drive? Yes. Nowadays, no. You are using
Solid
It's not solid state.
it's a
flash.
solid. Flash is a solid state drive disk. It's different from the traditional hard disk drive, which has
Group of flash drive, right?
group of, I mean the traditional hard disk drive, which has
Sectors.
That's yeah, magnetic.
90.
disk, which has the disk. But long time ago, your hard disk drive also has the magnet base. Okay? So using the magnetic tape, like have you ever used a cassette tape? No? Never ever? So when I was the 20, until that time, so I used a cassette drive. So it's from made in Japan. It's a Sony Walkman, which is called which was very it's more popular than the MP3 at the time. Everybody keep the Walkman like this size. It has the magnetic tape, so you can store the data in the magnetic tape also. How? How can you store your file in such a magnetic tape? What about your credit card? So nowadays it's changed using the IC chip, but still it has the magnetic tape. You can read and write, okay? Even you can copy this one. How? Because you can, as long as you can represent 0 or 1, okay? 0 means nothing and 1 is a whole. If you make something different, it can be used for storage. So it's the same thing with the magnetic tape. We can store the data. Okay? Such a magnetic tape still used for what? It's a backup purpose because its problem is a sequential search as well as slow. But it's a cheap and also very relatively reliable media. How much do you believe such a hard disk drive? What about the flash drive? Flash drive, even though there's no power, so you do not lose the data forever. No. At certain time, you will lose the data, even flash drive. That is the limitation of the flash drive. It's not anyway memory. So what about the hard disk drive? That has the CD from like this one. Have you ever seen you have seen in the database course, right? The previous class we discussed the same topic. Okay? What is this? This is the anatomy of your hard disk drive. If you deassemble your hard disk drive, you will see such a CD-ROM. This is exactly the same as your. Still, is there anyone who used the CD-ROM to listen to music? I'm using because my car is old-fashioned. It doesn't have any special port, so we need the CD-ROM. So it has exactly the same as actually the CD-ROM. How can you read listen the music using the CD-ROM? It can represent analog data actually. Okay, but we are talking about the digital data. Digital data is a 0 or 1. If you make the whole, okay, that is 1. Otherwise, it's a 0. Okay, so if you can represent there is a header. I think that this slide is not better than the operating system. There is a header. This is called the disk arm. There is a header. This header can be either whole or closed, 0 or 1 data. Then there are a bunch of holes along the track. Okay, you have so many tracks. So usually when you write the data, it's from outside to inside. You can write the data. Why don't you think about the burning a CD? Okay, that's the same mechanism as this one. Then you have the spindle, which means it makes your disk spin, rotate. So and this disk arm is moving forward and backward. Finally, it can read the data from your disk. That is the hardware mechanism to read the data. Write the data is the same thing. When you write the data, it can make the whole to either 0 or 1. Okay, that is the hardware. Then there's a CPU. the CPU as the, so there's an input and output. So during the input and output, CPU cannot do anything. So there might be the context switch and also interrupt. Then the CPU will, operating system will ask this controller to read the data with the information about the address, track number, cylinder number, and the block I. Actually, it is the symbolic address like the integer I. It can be converted into the physical address. Then this controller knows how to access this one. So rotate and find the data, and this one is based on the block. Okay, so that is the block. What is a block? Block is the basic input and output unit. So even though you need just the I integer I 4 bytes of the data, entire block will be returned. Okay, then this control, when this control receives the data and interrupt the operating system, then return this data to the memory. Okay, then the CPU scheduler dispatcher will select the next time. So this process will move to the from the wait queue to the ready queue. Then finally CPU can read the data. This is the basic mechanism how to read the data and how to write the data in the hard disk drive. Okay, I think that you guys know this one very well. I'm not going to discuss the details, the performance of the such a hard disk drive. What is the unit to measure the performance of your hard disk drive? No. When you buy the hard disk drive, what do you consider?
RPM.
Size and RPM. RPM means rotation per second? Minute. So 1 minute, how much? Because if you see that this one, to access the data fastly, it should rotate very fast. Okay? Otherwise, it will take a time. So what is currently the technology?
7,200.
7,000, I think the higher than that. Nowadays we have the higher than the 10,000. But the faster the better, not always. Okay, so it's there should be the optimal. So 7,500 is the typical nowadays based by country. But the current technology is up to the more than the 10,000 the RPM. Also because even though it's fast, the move rotate fast. So if your discount cannot locate the proper location, you may not get the full benefit. Also, there's a waste of the others energy. Okay. Then, as you have seen in the this one, when you find the data, there are two types of the latency delay. One is you need to find the address, physical address 6 times. Okay, 6 times and physically rotate and place the location. So that is called the access latency. So average wait. So there are two. So one is the 6 times, the latency, delay time, and other the latency. Okay. So total, the average I/O time include the average access time, okay, and also transfer rate, transfer time, and controller overhead. So we need to consider these 3 latency together. That is the reason to read data and write the data from the hard disk drive is very, very slow. Okay. What about the solid state, the disk drive, SSD? There is no rotational latency. That is one of the benefits using such a SSD. So it's a faster and also smaller. Okay? Because it does not have such a physical mechanism.
So the seek time is the looking for the address, right?
Yes.
And the average latency is
Yes. It's the rotational latency, and moving forward and backward is another the latency, but it's totally considered as the average latency. Also, controller managed all the read and write input and output, and also the inform to the operating system. That's altogether controller overhead. So solid state disk SSD, okay. So reliable than hard disk drive. Problem? Expensive. Okay, it's much expensive than the traditional hard disk drive, which is based on the CD. So, but the disk storage box still use the traditional hard disk drive. Okay, but it's much faster. So if you are struggling with such a performance issue, why don't you consider the SSD for your hard disk drive? There's no the rotational latency and no stick time to position.
So how does it store the data?
How to store the data is in SSD. That is based on the memory. Okay, it's basically the same as the memory, the addressing. Okay, so but it consider it has something technology which I do not know to keep the data without power, but it's not permanent. At certain time, you will, it's 20, 30 years, you will lose the power for such an SSD. Magnetic tape nowadays is only used for the backup media, still used, but the main problem is the slower, and also it supports the sequential search. Sometimes it's called the LTO N number. Okay? So if you see the LT or LT tape or the LTO, that means there's something like that. Considering the size of the media, so it's very cheap, the media to keep. Okay, then there are two types of the hard disk drive, and one is raw device, another one is a file system. When you store the data in the hard disk drive, so considering the hard disk drive, the CD-ROM type, it has the track, and each track has the sector. Each sector, you can store the data based on the block. This block is a fixed size. However, the sector can be various size. So sometimes you can put only one sector, or sometimes multiple. One for the sector, you can put the one block or the multiple block. So that is the blocking. Then, if you want to use directly this block to store the data, that is called a raw device. On top of that, it's very hard to manage. You should know each sector number, track number, sector number, and the block number. And for each block, you need to manage input and output. So not easy. So why don't we use the software that is called the file system? Some of the operating systems still use the raw device. Why? It's fast. Okay? Even though it's hard to manage such an input and output, but still use for that. Otherwise, you can use the file system like the F1632 and the NTFS. That is a file system that we are going to discuss the detail the next few chapters. Okay. So such a block is a logical concept. It's our data structure, basic unit of the data structure in the file system, file management and the storage management. Then such a hard disk drive should be attached to the computing architecture through the disk controller. So depending on the types of disk controller, it has a SCSI and a fiber channel. If that support the fiber optics, it's a fiber channel, a controller, and so on. nowadays we have the storage box. Sometimes it's called the storage box, storage array. It has many the hard disk drive inside the box. So that is called the storage array. So that will be, it's not, the RAID is not used a lot. We will see what is the RAID later. But nowadays, because due to the cheap price of the hard disk drive, we mostly use the mirror and stripe. The mirroring is good enough. So even though that utilization is 50%, we will see details what are they. Nowadays, we do not use a lot for such a RAID storage. I think I gave the example of the price for such a storage array, storage box, comparing to 20 years ago. So when I was a database administrator, we purchased a 36 gigabyte EMC storage box. So which is mirrored, which means actually 72 gigabyte, but because of mirroring, so mirror is the duplicate the data. We will see details. So capacity is utilization is 50% only half. So it's 36 gigabyte. You know how much it was that? It was the $300,000 20 years ago. It's almost 6 times of my yearly salary at that time. Only 36 gigabyte storage box. But nowadays it's very cheap, so even you can purchase 1 terabyte, so 70, 60. It's a 70 bucks, the 60 bucks for 1 terabyte. Okay, so that is different nowadays, which means you don't have to worry about too much for the storage management nowadays. So, however, if that is very expensive, there are a lot of algorithm technology to increase the utilization and to keep the performance. But because of the cheap price, it's not very important nowadays. However, such a storage area network is getting important because we have more and more servers. However, we'd like to integrate, consolidate the storage box into one, okay, using such a cheap storage array. So how can we implement such a thing? Which means from the local server we have the number of the computer server. Then we have the very expensive and very big storage box. So can I chop the hard disk drive array then distribute for each server? No, that's not possible. Instead, we can connect all the server to the storage using very fast media. Then from the each server point of view, it looks like the local. It looks like the connected to the bus, local bus. Then which one is the fastest one? This one. How can we connect? That is fiber optic channel, the FC. So using the fiber optics, it's very fast. It looks like almost the speed as the local bus. So from the computer, it doesn't look like the remotely connected. It looks like local server. What is the benefit? Using such a storage area network, so we can get the benefit of the storage array. Now, one of the benefits of the storage array is we can dynamically change the allocation for each server depending on the time. So during the daytime, online transaction or web server need more space. During the night time, we need the file server. We need more file server. We can dynamically change from the one storage array, storage box. Okay, then they are connected to the storage box. That is the idea of the storage area network. On the other hand, we have the NAS network attached storage. We consider the storage as one server. It looks like a computer. Just like when you communicate from this computer to other computer, we did in the, don't think we did, we implement the UPC or TPC. So using, for example, the TCP/IP, okay? So we should know the IP address and the port number and the connector router and using the root, okay? Routed root, then we can find the destination. Exactly the same mechanism for the storage box. So which means we need to specific router which is called the NAT, N-A-T device. So NAT is the storage, the router. So then all the computer is connected to all computer and storage box is connected to that device. Then this NAT device worked as the router. So whenever you access the data in that storage, so NAT device storage will route the way. It still use the local area network, just the gigabit Ethernet or the 10 gigabit Ethernet. So it's still slow comparing to the fiber optic channels. So now the SAN is still more popular than the NAT. So this is an example of the NAS. So they are connected. They have the this is good for when you have a number of storage or storage box, okay, not the consolidated big storage box. Then the main problem of the storage management is, for example, when you access the data. So this is a cylinder. Okay. So there are requests, a number of requests to access the data. So block I number 0. Next one is 1. Next one is 5. Next one is 10. Something like that. This one will be actually sector number converted to the sector number. This track, specific track, okay, and sector number converted to, actually it's not block ID. Symbolic address converted into the sector number, okay, sector number and block ID. This sector number is consists of the track as well as the block ID number. Okay, does it make sense? Block ID number and sector number and the track number. Okay. Then how can you find the data? You have the disk head. Disk head is moving forward and backward, and this one is rotating. So there are two things you need to consider when you access the data: how long it takes to rotate the data, and how long it takes to find the track number, right? So at that time, which one will be faster? Rotating and moving forward and backward. So 7,500 per minute means how many rotation per second? So 100, more than 100, right? So 100 rotation per second. And this one is moving forward and backward, should be slower than this. So when we schedule, when we have the request of the block number or the symbolic whatever, the data, when sometimes the data is here, data is here, data is here, data is here. Actually, the rotational latency, delay due to the rotation is a very small amount. The main issue, main delay is how long it takes moving forward and backward to your disk arm. So we are going to consider the delay time of your moving. The disk arm is moving forward and backward. Then try to find. That is the code. I think I got mistake the last time. Seek time is rotational latency is rotation. It takes a time to find the location of the sector by rotating, and seek time is the specific track number by moving forward and backward. Then the other disk controller and the other the latency, average waiting time. So we are going to consider seek time. Okay. What is the problem? Is the less seek time is better or the longer seek time is better? Definitely less seek time is better. But think about if we have the data is here. So what is the best way? If we can access the data by moving 1 times of the forwarding. That will be faster, right? However, if the data is here, moving forward and backward, it will be slower. That is the problem of the disk scheduling. So in this disk scheduling, we try to find best performance of scheduling, how to schedule, how to order the request of the block to read and write the data in the queue. Okay? How to find the optimal path of the moving forward and backward of your disk arm. That is called the disk scheduling. Okay. But when we schedule such a disk scheduling, we are not going to consider the rotational latency because that is the small amount comparing to the seek time. In other words, the disk arm, speed of the disk arm. So, for example, let's say that we have the 200 cylinder, okay, in the request queue. 200 cylinder means yes. So our problem is, so this is the number of the cylinder, okay? From the, let's say we have the 0 to 199, 200 cylinder. Cylinder means from the, this is the hard disk drive, okay? This is the spindler. So we have the 0 to 199, the cylinder number. Okay, so for example, first we have the request 98. So this column will be positioning like this way. Then next one is 183. 183 is the here. So moving forward. Then 37 is here. Next here. And 122 is here. So moving forward. Okay. And the 14 is here, backward, moving backward. Then, what is the total, the seek time? Total seek time is total distance of moving disk arm. So for example, from the 98 to 183, then moving back the 37 and 22 and 14, 124. So sum of total moving distance is the seek time. Our problem is, can we minimize, decrease such a moving distance? Is there any way? So in this case, we have head pointer is a 53, which means this is a 0. Let's say this is a 0, 199. The head is on the 53. Okay, then in your request queue, we have the address 98, 183, 37. This is actually cylinder number, track number. Okay, so next one doesn't have to be 98. If you can find the shortest path, so depending on how to schedule to access the data, okay, that is a disk scheduling algorithm. So what is the simplest way? First in, first out, which means the 98 is the first in. So we will access the 98 first. Then 183, 37. Obviously, this is not the optimal solution, but simple solution is working because it's simple to implement. So that is the first in. First come, first serve. The disk scheduling algorithm. Okay, so let's see. So in the queue, we have the 1, 2, 3, 4, 5, 6, 7, 8. 8 requests. Okay? Then the current head position start 53, which means our disk arm is like here. Okay? Then the next one is 98. So 98 here, this is the distance. So how much is that? 98 minus 53.
45.
So 45. Okay. Then next is 183. 183 is here too. Here. So 183 minus
85.
so 98. So something.